All right, guys, welcome back for another lecture video. This is number 4 for chapter 10 here, and 4, but also the last one for chapter 10 here. And the last thing we're going to focus on here, it's a couple of cleaning up of things, but more importantly, this last chunk here is based on how to name formulas, right? So naming binary compound or binary covalent compounds, right? Covalent molecules. So we did something similar, obviously, with our ionic bonding chapter, our ionic, molecules, ionic compounds chapter, where we had to look at a formula, right? So let's say we were looking at a formula like MgCl2, right? And we had to determine how to get the this whole setup here, MgCl2, to turn into the words magnesium chloride, right? And then vice versa, right? How to take the words magnesium chloride and convert those words into MgCl2, right? Now, it ends up kind of being pretty much the same here, but we use a couple of added things here. So for covalent molecules, name depends on the number of atoms and not the charges, right? There are no ions. There's no charges present in covalent molecules, right? So for that reason, we can't leverage that crisscross rule that we were previously using, right, to crisscross the charges down to become our new subscripts, right? We can't do that because there are no charges. So what we do instead here is we count the number of atoms, okay? And the catch here is that we get to, once again, I know we've been introducing a couple of new tables to our at our disposal here, but we get to use a new table here, okay? And it's table 2 from page 13 titled covalent prefixes. So this whole table right here gives us a ton of information based on the number of atoms present in the actual formula and then the prefix associated with that particular atom. Okay, so it's pretty straightforward. Okay, you count atoms and you use table 2 to count your number of atoms and then determine the prefix associated with that particular name. Okay. So the first element in the compound, first using the entire element name. Okay. The second element in the compound then uses the last that IDE ending comes back into play here, right? And then for both the first and second element, use the appropriate prefix before the name to indicate the number of atoms, okay? Now, there is one exception, and I'll talk more about, obviously, examples of doing this because we'll do them in class, and more about this exception. But just know that there is an exception present here. If there is only one atom present of the first element only in the formula, no prefix is needed, okay? So I'll show you more about that in general, okay, in the future. Here is like a basic or a slightly different version, slightly different look in terms of the look of it, but everything still amounts to be the same here, right? So table 2 was essentially converted into, from this table here, 8.3. I know it says memorize here. It says memorize prefixes in covalent molecules and covalent compounds. You don't need to do that, right? Obviously, it used to be something that we had you guys focus on in terms of memorizing these prefixes, but that is not something that we're going to really have you guys concerned with. So that's why we give you table 2 now, right? So this idea of memorizing the prefixes, not necessary because everything you see on this screen here, everything I need you to know is present right there on table 2 for you, okay? So no need to memorize anything. Don't freak out, okay? Now, couple of housekeeping things to kind of finish up covalent compounds here, right? 2 more slides here, and then that's it. So two more slides. Pretty quick video today. But this idea of covalent compounds are the same thing as a molecular compound, and we're going to get more of that in the next slide here. But covalent molecules and covalent compounds can exist as solids, liquids, or gases, right? So of a wide array of different essentially states of matter, right? And you kind of compare that to some of the properties of ionic compounds, for example, right? Where more often than not, ionic compounds really only do exist as solids, right? They're not really going to exist as liquids or gases, okay? Whereas covalent molecules can exist as solids, liquids, and gases, okay? More often than not, they really do exist oftentimes as liquids and gases, sometimes solids depending on how they're set up, but it's pretty often that they're going to be liquids and gases specifically, okay? They're often much softer than ionic or even metallic compounds, right? So these ideas of metallic and ionic compounds being very, very strong and hard to break or hard to, change their malleability is pretty consistent with ionic, whereas that's not so much the case with covalent molecules, right? They're often much softer and more brittle and easier to break compared to ionic or metallic compounds, right? They're also going to be very poor conductors of heat and electricity, where on the flip side, okay, ionic compounds and also metallic compounds, much better conductors of heat and electricity, okay? Not only that, but once again, almost pretty much the exact opposite of ionic compounds, right? These covalent molecules have low melting and low boiling points compared to our ionic compounds that have higher melting points and higher boiling points, okay? So again, we've talked about this several times, and this is no different here. The difference between ionic compounds and covalent molecules, they're almost exact opposites from each other in so many different ways. And the physical properties are another example of that, right? So all of these physical properties here for covalent molecules are basically the opposites of what already exists for our ionic counterparts, okay? Last thing here is different types of formulas here, right? And this is going to kind of be the start to kind of show us some specific things we're going to get into next chapter, which is our next chapter, chapter 7, as well as a chapter that's going to be a little bit down the way later on this school year, okay? So there's three main different types of formulas. There are empirical, molecular, and structural formulas, okay? One of these structural formulas are ones you've basically done before, right? Structural formulas are basically Lewis structures, all right? So it's at least convenient in that regard there. But this idea of an empirical formula and a molecular formula are pretty hand in hand with each other, okay? An empirical formula is the simplest ratio of atoms in a compound. For ionic compounds, this is always the case, right? Because as we know, let's say, for example, we had a situation where we've got Mg2Cl4, right? Our ratio of atoms here for magnesium atoms to chlorine atoms is 2 to 4, right? And if we recall from chapter 5, our goal here was to always reduce this ratio of atoms down to its most simple ratio, right? So if we have a ratio of 2 to 4, we can actually simplify that to a ratio of 1 to 2. Okay, that's why our formula of MgCl2 is MgCl2 and not Mg2Cl4, right? So we get rid of that 2 there, and that 4 turns into a 2, MgCl2, right? Because our ratio is reduced down, right? Now, right, whenever you look at a molecular formula, that is the actual ratio of atoms in a molecule for covalent compounds without having to worry about reducing that ratio. Oftentimes, guys, when it comes to molecular formulas in covalent molecules, we are actually not going to be doing any reducing, right? So it's not like it is for ionic compounds, right? Ionic compounds, we were always reducing to the lowest ratio. When it comes to our molecular compounds, right, like our covalent molecules here, we are not going to reduce ratios, right? That's why we have two different types of definitions here. A molecular formula where we're not reducing the ratio, right? It's the actual ratio. And then the empirical formula, which it is the reduced version of it, okay? There are applications to both, however, right? That's why we have a definition that we use and talk about both of them, right? The molecular being the actual and the empirical being the simplified ratio, right? And again, next class when we meet, we do some examples of them, you'll see why it's important to have both, okay? And then again, lastly here, your structural formula, it shows the arrangement of atoms in space. It's basically a Lewis structure without any of the added dots there, okay? So again, pretty straightforward. But that about does it today for our video. I will see you guys in class. Take care.